else.
And I like all the colors of all the actual potential curves. And do you see how the color, like for example, the atrial muscle coordinates with that green P wave down there?
Mm-hmm.
It's a great event.
And then here's a sinus node. You can see it's right here at the beginning. I really like this picture. I wish I could use it. Anyway, so now that we know about this, remember we're primarily going to deal with either surface ECGs or bipolar signals at this point, okay? We have several different types of filters, and remember these were created by engineers, and they have their own language because they're elitist snobs just like we are, and therefore none of this makes any sense to us. So we have a high-pass filter, and what does that mean? That means it lets all the high frequencies go past it, but it filters out the low stuff. So when you see the word high, it gets rid of low frequency. All right? This really is all about getting rid of patient movement, muscle isopotentials, respiratory wave interference, that sort of thing. Okay? Our low pass lets all the low signals go by and actually gets rid of all the high stuff. And the high stuff I like to refer to as schmucks. It's your cell phone towers, it's noise coming off of your computer circuits, it's very high frequency noise, and it's stuff that we normally see coming from electronic equipment and or radio, television, cell phone, radio wireless. Okay? We also want to talk about the notch filter. This is a special little filter. In our country, we use 60 hertz. Are you guys on a 60 hertz system?
Yes.
Okay. So this is going to be big for you guys too. It's designed to fill out AC current noise, just stuff coming from you plug something into the wall and it goes to the computer. It also comes from fluorescent lights, big time from fluorescent lights. And it literally just filters out everything that's between 50 to 60 hertz. We use it all the time on our surface ECGs because it's out in the open and most of the signals we're looking at aren't part of that particular group. Okay? The problem we have, and it took a long time for me to actually put this together, but our bundle of hiss actually runs between 40 to 60 hertz. Think about that for a minute.
Is that why we weren't seeing any bundle of hiss? Because you had the notch filters on?
No, that was my physician being lazy, and you know who that was. And this is a common thing I see. I've got noise on my tracing. Turn on the notch filter. I can't see my hiss. Gain it up. What they did specifically, because a lot of the noise that you see isn't coming from 50 or 60 hertz, it's coming from somewhere else. They've literally crimped their hiss tracing and then made the signal big and amplified all the stuff that was actually causing the noise. And then they wonder why they can't get any signals, and then they call me and have to spend lots and lots of money for me to come in and troubleshoot their lab and tell them they don't know what they're doing. All right. Atrial to ventricular signals are somewhere between 10 to 50 hertz. We can use the notch pass filter on them because they're really strong signals if we need to, and it's not that big of a deal. But when we're getting around the bundle of hiss, we're going to run into some problems. Also, remember what the hiss really is. It's a pathway. So if you're looking for a pathway along your annulus, and you've got your notch filter on, you think you'll see the pathway? No. Now the good news is, and if we get time, I'll show you one or two tracings from Nicaragua that actually show this. You really don't care, because you get good signals from the A and the V that converge anyway. So we only see that Kent potential is what that little pathway is called. Maybe 1 out of 10 times. It makes us really happy. We congratulate each other. We open a bottle of champagne. We take snapshots, send it to our friends and family, put a picture of it up on our refrigerator for mom to see, that sort of thing.
Facebook.
See, now you're trying to show how old I am. All right? I start talking about the refrigerator, and you're talking about Facebook. You're on my list, young man.
That was Michael Polo today.
No, it was the top. Spinning the top.
What is that?
All right. So keep that in mind. I believe in actually using all these different tools to help you. I don't believe in the carte blanche statements of doing things. All right? If you talk to GE or any of the company, they're going to tell you don't use a notch filter on your cardiacs. I disagree. If you need to use it, use it. But apply your knowledge intelligently, not because somebody told you to flick a switch or someone says this is the way it has to go. Yes, sir?
I want to ask you about these filters. Is it like for everything, or every electrode has its own range?
Every signal has its own filter setting. Every channel. All right? And based on the type of signals, you change them. If we're bipolar, they're one setting, and we'll go over that. If they're surface, they're another setting. And then if they're unipolar, I can get into a whole 3-hour conversation and argument with a doctor on what's right. So, all right? All right. So the idea is we're trying to box in the signals so that we get what we want. Okay? We don't need the high schmutz, and we don't need the low movement. And then if necessary, we're going to take a little blinder and put it right across in front of everything to get rid of the sunlight that's glaring in our eyes. Okay? So this is just respirations. You can actually see this on an intracardiac if your high pass filter isn't set correctly. I set it correctly, and all this up and down movement that's going all over my screen turns into a nice pretty flat line the way it's supposed to, except for when that little local activation tissue fires off. All right? This is artifact, or schmutz, or noise, or whatever term you want to call it. Usually the physician has some choice verbiage for it, depending upon what country you came in. You might learn to swear in a new language. But this is what you will see. You will see the schmutz. And we set our low-pass filter to the right setting, bringing that box down narrow. We'll get rid of it, and now we'll have a nice, pretty signal the way we're supposed to. Make sense? Now, we have another thing, because remember, we talked about frequency, right? Well, we also have amplitude. And these signals are, even though they're strong, because our hearts are strong and all that, they're very small. The amplitude is actually very small. We're literally only trying to capture, a couple, like about 1,000 cells doing something. Okay? Very small electrical field that's coming off of just these little localized tissues. So the amplifiers are designed, and that's why they call them amplifiers, to amplify these signals. My company is the only company on the market that allows you to adjust that amplification. And that's one of the reasons I want you to understand, not because I'm trying to sell you my company's equipment, but if you're using a GE piece of equipment, that amplification can get you into trouble if you think it's something else. Because what it's really doing is it's setting the sensitivity of the electrode pair. And the reason I did well in the EP lab working with this equipment initially was I was a concert promoter for a couple of years in Detroit, and I was bringing bands in from Europe. And running the amplifier in the Cardiolab system was the same thing as running the soundboard for a concert. And that's how I figured this out. My lead singer was like the sinus node. All right. The lead guitarist was the AV. Bass guitarist was the ventricle. And the CS was the horn section. All right. I'm sorry, it's still insane. Okay. So, and what we wanted to do is we wanted to see what we needed to hear them, but we didn't need to hear the audience or everything else that was going on. So we would sit at our control and change the sensitivity of the microphone until we could actually hear just them. And that's what we're doing with gain. We're changing the sensitivity of the electrode pair so we can see just what we need to see.
That's a good analogy.
And like I said, this is for our customers. Usually they're having problems and I'm trying to correct them of their bad habits. So this is what I like to say. We don't increase the sensitivity or the gain. because of poor catheter position, bad eyesight on the part of the physician. The monitor is too far away or the monitor is too small. All right? It's not the reason to increase your sensitivity. Scale is the exact opposite. Scale is like me turning up the volume on my speakers. So I've got everything set so I can see everything, and then scale is like just making it big enough so everyone in the room can hear it. Scale specifically just draws it bigger. All right? So if I have a nice clean signal and I draw it bigger, it's going to be a nice, clean, big signal. If I have a really, really noisy signal and I make it bigger, I have a really, really big, noisy signal that's not doing me any good. You see what I'm talking about? And this was the big important thing, because I've actually done this where I put in all the settings where they're supposed to be, then up the scale on our system. And then they go in there and the doctor's like, these are some of the best signals I've ever seen. And I'm like, get him some new glasses. Because it can compensate for bad eyesight, too small monitors, or the monitor is too far away. I actually have a lot less trouble if they're not using our monitors, but they're using one of those great big, huge, massive, multi-screen, NASA, CIA, drone dropping, whatever the heck it is that thing is, you know what I'm saying? It's like I want it in my living room so I can watch the new Thor movie when it comes out next week. All right? So, because they put the signals up on the screen much bigger than on the little monitors that we supply with our equipment. I have almost no problems with sites that do that. All right? So gain versus scale, this kind of is a big deal. This determines how the signal is recorded, because that's how it's going to record it, and it's for the rest of eternity, or at least until somebody drops a magnet on the computer. All right. All of our signals are set to 1,000 for a gain, except for the hiss and the ablation, because we are looking for smaller signals, and we set it to 2,500. Any setting above 2,500, low-level artifact is going to be present. They call me and complain about noise on their system, and they tell me that their gain is set at 5,000 or 10,000. I tell them their gain is set wrong. Call me back when you set it up right, and the conversation is over with. I will not address noise issues with a site if they have their gain settings incorrectly. And I'm not saying that you can't use this, but you have to make sure that your lab is a very clean, well-built, electrically stable room. There are many different places, like I was saying, some of our research groups, that they're looking for very small signals. They have very clean rooms, and they're using 5,000 and 10,000 all the time so that they can see things and do research on stuff that we haven't even thought about trying to use clinically yet. Okay? I tell them they're always available to increase for spot check. Remember how I said unhealthy tissue, low amplitude? Spot checking when you're doing a VT ablation and you're looking to say, is this really a signal or what? Bumping it up a little bit, going, yeah, that's real signal, then bump it back down. See what I mean? Scale on ours is a global setting. It's basically what will show up on the live screen and also on the review screen. But on the review screen, scale is signal specific. On the live screen, it's globally. If I change the scale on the live screen, all the signals get bigger. On the review screen, it only changes the scale on the one that I'm working on. Okay? It doesn't add artifact, but it will exacerbate existing artifact. If you have crud going in and you make it bigger, you just have bigger crud. Does that make sense? Mm-hmm. The default on our system and most systems is 1/16. But almost all the other systems don't allow you to mess with their gain settings. You only get to mess with their scale. And I've seen on a lot of other systems the standard that everyone's using is 1/8 or 1/4. Because they all want big signals so that they can do the case faster and get on to the next case. Change is geometric, because 1/8 to 1/4 is twice as big. 1/4 to 1/2 is 4 times as big as your original setting. So it doesn't just go like this. It goes, okay? So it's a very powerful tool. Be careful with it. I pulled something. All right. Yeah, let's switch to the other one now.
Okay.
Am I on time or?
Well, yeah.
Okay.
They